Hello students, today I will discuss about the chapter 3 of the class 11 NCERT, which is the structure of atoms. It is very important for understanding the chemical reactions in further. The atomic theory of matter was first proposed on a firm scientific basis by John Dalton, a British school teacher in 1808. His theory, called Dalton's atomic theory, regarded the atom as ultimate particle of the matter. In this unit, we start with the experimental observation made by the scientists towards the end of the 19th and beginning of the 20th century. These established that the atoms are made of the subatomic particles, that is, electrons, protons, and neutrons, a concept very different from that of Dalton. First come to the cathode ray tube, and second come to the cathode ray tube with perforated anode. The results of these experiments are summarized below. The cathode rays starts from the cathode and move towards the anode. These rays themselves are not visible, but their behavior can be observed with the help of a certain kind of materials such as fluorescent or phosphorescent with glow when hit by them. The television picture tube or cathode ray tube and television pictures result due to the fluorescence on the television screen coated with a certain fluorescent or phosphorescent material. In the absence of electrical or magnetic field, these rays travels in a straight line. In the presence of the electrical or magnetic field, the behavior of the cathode rays are similar to that expected from negatively charged particles, suggesting that the cathode rays consist of negatively charged particles called electrons. The characteristics of cathode rays do not depend upon its mass also. Charge to mass ratio of the electron. In 1897, the British physicist J.J. Thomson measured the ratio of the electrical charge to the mass of the electron by using the cathode ray tube, applying the electrical and magnetic field perpendicular to each other as well as to the path of the electron. By carrying out the accurate measurement on the amount of deflection observed by the electrons on the electric field or the magnetic field strength, Thomson was able to determine the E/ME value as 1.75820 into 10 to the power 11 coulomb per kg. This is the apparatus. This is the apparatus of determining the charge to mass ratio of the electron. The charge of the electron. R.A. Millikan devised a method known as the Waldorf experiment to determine the charge on the electron. He found the charge on the electron is to be minus 1.6 into 10 to the power minus 19 coulomb. The present accepted value of the electrical charge is minus 1.602 into 10 to the power minus 19 coulomb. The mass of the electron was determined by the combining the result of the Thomson's value of the E/mc ratio. So mass of the electron is equal to found to be 9.11 into 10 to the power minus 31 kg. Here are the below given a demograph of the Millikan's Waldorf experiment apparatus. Discovery of proton and neutrons. Electrical discharge carried out in the modified cathode ray tube led to the discovery of the canal rays carrying positively charged, and the characteristics of the positively charged particles are listed below. Unlike cathode rays, the mass of the positively charged particles depend upon the nature of the gas participant in the cathode ray tube. These are simply and positively charged gaseous ions. The charge to mass ratio of the particles depend on the gas from which these originate. Some of the positively charged particles carry a multiple of the fundamental unit of the electrical charge. The behavior of this particle in the magnetic or electrical field is opposite to that observed in this electron or cathode. The smallest and lightest positive ion was obtained from hydrogen and was called as proton. The smallest and lightest positive ion was obtained from hydrogen and it was called as proton. The positively charged particle was characterized in 1919. Later, a need was felt for the presence of the electrically neutral particle as one of the constituents of the atom. This particle was discovered by Chadwick in 1932 by bombarding a thin sheet of beryllium by alpha particle. When electrically neutral particle having a mass slightly greater than that of the proton were emitted, the name of these particles are as neutrons. Atomic models. Dalton suggested an atomic models to account the stability of the atom, to compare the behavior of the element in terms of both physical and chemical properties, to explain the formation of different kinds of molecules by combination of different atoms, to understand the origin and the nature of the characteristics of the electromagnetic radiation absorbed or emitted by the atom. This is the Thomson model of atom, watermelon model of atom. It is palm pudding resin model. Here is a positive sphere and the electron is put into this positive sphere as the seed of the watermelon. Then come to the Rutherford nuclear model of atom. Rutherford and his students bombard very thin gold foil with alpha particle. Rutherford's famous alpha particle scattering experiment is this. So here is a source of the alpha particle. It is the lead plate and it is the gold foil here and the thin surrounding the foil, gold foil. And from this Rutherford model of experiment, the following results are obtained. The result: most of the alpha particles passed through the gold foil is undeflected. A small fraction of alpha particle was deflected by small angles. A very few alpha particles bounced back, that is, were deflected nearly 180 degree. Inference of these results. So inferences are: most of the space in the atom is empty as most of the alpha particle passed through the foil undeflected. A few positively charged alpha particles were deflected. The deflection must be due to the enormous repulsive force, showing the positive charge of the atom is not spread throughout the atom as Thomson had presumed. The positive charge has to be concentrated in a very small volume that repelled and deflected positively charged particles. The calculation by Rutherford showed that the volume occupied by the nucleus is negligibly small as compared to total volume of the atom. The radius of the atom is about 10 to the power minus 10 meter. The radius of the atom is about 10 to the power minus 10 meter, while that of the nucleus is 10 to the power minus 15 meter. One can appreciate this difference in size by realizing that if, on the basis of the above observation, Rutherford proposed the nuclear model of the atom. According to this model, the positive charge and the most of the mass of the atom was densely concentrated in an extremely small region. This very small portion of the atom is called Nucleus. The nucleus is surrounded by the electrons and that move around the nucleus with a very high speed in a circular path called orbits. Thus, the Rutherford's model of atom resembles the solar system in which the nucleus plays the role of sun and the electrons that of revolving planets. Electrons and the nucleus are held together by electrostatic force of attraction. Developments leading to the Bohr's model of atom. Historically, the results observed from the studies of the interaction of the radiation of the matter have provided the immense information regarding the structure of the atoms and molecules. Niels Bohr utilized these results to improve upon the model proposed by the Rutherford. Two developments played a major role in the formulation of the Bohr model. These were the dual character of the electromagnetic radiation, which means the radiations possess both wave-like and particle-like properties. Number 2, the experimental results regarding the atomic spectra. Here it is the spectrum of the electromagnetic radiation. Here the electric field and the magnetic field are mutually perpendicular to each other. Here is a series of the spectrum from gamma rays to long radio waves. The visible spectrum lies between 400 angstrom to 800 angstrom, a small part of the entire program. Now come to the Max Planck's sum experiment. A black body radiation. A black body is also a perfect radiator. Arrived at a satisfactory relationship by making an assumption that absorption and emission of the radiation arises from oscillator, that is, atom is the wall or black body. Their frequency of oscillation is changed by the interaction with oscillators of electromagnetic radiation. The Planck assumed that the radiation could be subdivided into discrete chunks of the energy. He suggested that the atoms and the molecules could emit or absorb energy only in discrete quantities, not in the continuous manner. He gave the name quantum to smallest quantity of energy that can be emitted or absorbed in the form of the electromagnetic radiation. The energy of the quantum of radiation is proportional to its frequency and is expressed by the equation E is equal to h2. The proportionality constant h is known as Planck's constant, which has value 6.626 into 10 to the power minus 34 joules second. The quantization has been compared to standing on the staircase. A person can stand on any step of the staircase, but it is not possible for him to stand in between the two steps. The energy can take any one of the value. The energy can take any one of the value from this following set, but cannot take any values between them. That is, E is equal to 0, h nu, 2h nu, 3h nu, 4h nu, nh nu. Come to the photoelectric effect. It is proposed by the famous scientist Albert Einstein. He got a Nobel Prize for this experiment. The electrons are ejected from the metal surface as soon as the beam of the light strikes surface. That is, there is no time lag between the striking of the light beam and the ejection of the electrons from the metal surface. The number of the electrons ejected is proportional to the intensity of the brightness of the light. For each metal, there is a characteristic minimum frequency, that is nu zero, is also known as threshold frequency, below which the photoelectric effect is not observed. At a frequency nu greater than nu zero, the ejected electrons come out of certain kinetic energy. The kinetic energies of these electrons increased with the increase of the frequency of the light used. So here the experiment, here the tube, here the metal surface, here it is the light striking the metal surface, and the electron is ejected, which is detected by an ammeter deflection. Einstein in 1905 was able to explain the photoelectric effect using the Planck's quantum theory of electromagnetic radiation as his starting point. The minimum energy required to eject the electron is h nu 0, which is called work function or W0. Then the difference in the energy h nu minus h nu 0 is transferred as the kinetic energy of the photo electron. The following conservation of the energy particle, the kinetic energy of the ejected electron, is given by the equation h nu is equal to h nu 0 plus half me v square. Now come to atomic emission and atomic absorption. The first one, A, is excited sample passing through a prism, and the prism divided the light into a spectrum, and which is called an emission spectrum. And the second one is absorption spectrum, where the first one, the light is coming from a white light source, passing through the absorbing sample, and the light passing through the absorbing sample then passes through a prism, nickel prism, and the spectrum is got in a film or the detector, which is called absorption spectrum. So emission spectrum is obtained from the excited sample, and the absorption spectrum is from the white light source passing through an absorbing sample. The light emitted by a sample of excited hydrogen atoms can be passed through a prism and separated into a discrete unit wavelength. Thus, emission spectrum, which is a photographic recording of the separated wavelength, is called as a line spectrum. Any spectrum of reasonable size contains an enormous number of the atoms. Although a single atom can be in only one excited state at the same time, the collection of the atom contains all possible excited states. The light emitted as these atoms fall to lower energy states is responsible for the spectrum. Atomic absorption. The BS atomic absorption. When white light is passed through an unexcited atomic hydrogen, then through a slit and the prism, the transmitted light is lacking in intensity at the same wavelength as recorded absorption spectrum is also a line spectrum. Line spectrum of hydrogen atom can be expressed in the terms of wave number when the visible lines of the hydrogen spectrum obey the formula. The nu bar is equal to 109677 1 by 2 square minus 1 by n square centimeter inverse, where n is the integer to greater than 3. This series of lines is described in the formula is called Balmer series. Balmer series of line spectrum are only the lines in the hydrogen spectrum which appear in the visible region of the electromagnetic spectrum. The Swedish spectroscopic Jones Rydberg noted that all series of the lines in the hydrogen spectrum could be described by following expression: nu bar is equal to 109677 first bracket 1 by n1 square minus 1 by n2 square centimeter inverse, where n1 is equal to 1 2 3 4 etc. and n2 is equal to n1 plus 1 to 1 n2 n1 plus 2 etc. For Lyman series, n1 is equal to 1 and n2 is equal to 2 3 4 5 6 7 dot 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 dot. The spectral region is ultraviolet region. The Balmer series n1 is equal to 2 and n2 is equal to 3 4 dot 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 dot, which is visible region. Paschen series n1 is equal to 3 and n2 is equal to 4 5 dot 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 dot, which is infrared region. Bracket series is also infrared and Fund series is also infrared region. This is some transitions from Balmer series, Paschen series and Lyman series. Bohr's atom model postulates the electron in the hydrogen atom can move around the nucleus in a circular or fixed radius energy. These paths are called orbits, stationary states or allowed energy states. These orbits are arranged concentrically around the nucleus. The energy of the electron in this orbit does not change with time. However, the electron will move from lower stationary state to higher stationary state when required amount of energy is absorbed by the electron. Energy is emitted when the electron moves from higher stationary state to lower stationary state. The energy changes does not take place in a continuous manner. Number 3, the frequency of radiation absorbed or emitted when the transition occurs between the two stationary states that differ in energy, which is delta E, is given by nu is equal to delta E by H. Delta E is equal to E2 minus E1 by H, where E1 and E2 are the energies of the lower and the higher allowed energy states respectively. The expression is commonly known as the Bohr's frequency rule. The angular momentum of an electron is quantized. In a given stationary state, it can be expressed as an equation mvr is equal to nh by 2 pi. However, according to Bohr's theory of hydrogen, the stationary state for the electron are numbered as n is equal to 1 2 3 dot 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 dot. These integral numbers are known as the principal quantum numbers. The radii of the stationary state are expressed as r is equal to n square a0, where a0 is 52.9 picometer. Thus, the radius of the first stationary state, that is called the Bohr orbit, is 52.9 picometer. Normally, the electron in hydrogen atom is found in this orbit, where n is equal to 1. N increases, the value of the r will increases. In other words, the electron will be present away from the nucleus. The most important property associated with the electron is the energy of the stationary state. It is given by the expression E is equal to minus r 1 by n square. N is equal to 1 to 3, where the RH is equal to Rydberg's constant. Its value is 2.18 into 10 to the power minus 18 joule. Now coming towards the quantum mechanical model of atom. Two important developments which contribute significantly in the formulation of the such model are: number 1, dual behavior of the matter. Number 2 is Heisenberg uncertainty principle. The de Broglie equation, the wave nature of the particle for lambda is equal to h by mv, and the Heisenberg uncertainty principle, where the Warner's it stated that uncertainty principle, it stated that it is impossible to determine simultaneously the exact position and the exact momentum of an electron. Mathematically, it can be given as in equation x delta x into delta px is greater than or is equal to n by 4 pi, or delta x into delta mvx is greater than or is equal to m by 4 pi. In the case of the microscopic object like an electron, or other hand, delta v into delta x obtained as much as larger, and such uncertainties are real consequence. For example, for an electron whose mass is 9.11 into 10 to the power minus 31 kg, according to Heisenberg uncertainty principle, delta v into delta x is equal to 10 to the power minus 4 meter to the power minus 2 second to the power minus 1. It therefore means that if one tries to find the exact location of the electron, say the uncertainty only 10 to the power minus 8 meter, then the uncertainty delta v in velocity could be 10 to the power minus 4 meter square. Second inverse divided by 10 to the power minus 8 meter is approximately 10 to the power 4 meter per second, which is so large that the classical picture of the electron moving in the Bohr orbit cannot hold good. It therefore means that the precise statement of the position and the momentum of the electron have to be replaced by the statement of the probability and the electron has at a given position and momentum. This is what happened in the quantum mechanical model of the atom. The quantum mechanical atom model for a system, the Schrödinger equation is written as h cap psi is equal to a e psi, where h cap psi is mathematical operator called Hamiltonian operator. The Schrödinger gave a receive. An atomic orbital is an wave function psi for an electron in an atom. The probability of the finding of an electron at a point within an atom is proportional to the square of the orbital wave function, that is mod psi square at that point. The psi square is known as the probability density and is always positive. From the value of the mod psi square at different points within an atom, it is possible to predict the region around the nucleus where the electron is most probably found. Principal quantum number small n. The principal quantum number also identifies the shell. With increase of the value of the n, the number of the allowed orbital increases are given by n square. All the orbitals of the given value of n constitute a single shell of an atom. N is equal to 1, 2, 3, 4 is equal to shell is equal to KLMN. The size of an orbital increases with the increase of the principal quantum number. In other words, the electron will be located away from the nucleus, since the energy is required in shifting away the negatively charged electron from positively charged nucleus. Now come to azimuthal quantum number L, which is n minus 1. For n is equal to 1, L is equal to 0, n is equal to 2, L is equal to 1, and n is equal to 3, L is equal to 2. For example, when n is equal to 1, L is equal to 0, which is n minus 1. Each shell consists of one or more subshell or sublevels. Now come to magnetic quantum number M, small m. For a particular value of n and L, there is a magnetic quantum number, which is defined by 2L plus 1. For any subshell of defined L value, 2L plus 1 values of ml are possible. ml is equal to minus L minus 1 minus L minus 2 0 1 L minus 2 L minus 1 L. Thus for L is equal to 0, the only permitted value of ml is equal to 0. So for L is equal to 0, m is equal to 1. For L is equal to 1, M is equal to 3. For L is equal to 2, M is equal to 5. So subshells S is S. For the value of L is equal to 0, subshell notation S. Number of orbital is 1. For value for L value 1, the subshell notation is P, and the number of the orbitals are 3. For L value 2, the subshell notation is D. The number of orbitals are 5. For L value 3, subshell notation is F, and the number of the orbital is 7, and so on. Now come to electron spin or spin quantum number, which is stated as S. An electron spins around its own axis much in similar way as the Earth spins around this own axis while revolving around the Sun. In other words, an ms which can take a value such that plus half or minus half. These are called the two spin states of the electron and are normally represented by two arrows. The spin up, spin down. Two states of electrons are defined as ms values, plus half and minus half, are said to have the opposite spin. The orbital cannot hold more than two electrons, and these two electrons should have opposite spins. The total number of the nodes are given by n-1, and the sum of the angular nodes is given by n-l-1. And sum of L is angular nodes and n-l-1 is radial nodes. This is the pictures of the 1s orbital, 2s orbital, 2px, 2py, 2pz orbitals. These are the d orbitals: dxy, dxz, dyz, dx square minus y square, dz square. The energy of the order of the orbital: 1s less than 2s is equal to 2p, less than 3s is equal to 3p is equal to 3d, less than 4s is equal to 4p is equal to 4d, like that. The orbital having the same energy are called the degenerate orbital. N value higher, the energy is higher. If the n value same, then the L value is higher, the energy is higher. The screening of the effective nuclear charge, Z effective, the electron cloud screening power. The lower the value of the n plus L for an orbital, lower is the energy. If the two orbital having the same value of n plus L, the orbital with the lower value of n will have the lower energy. The Aufbau principle: in ground state of the atom, the orbitals are filled in the order of their increasing energies, from 1s to 2s to 2p, 3s, then 4s, 3s, 3p, 4s, 3d, 4p, 5s, next 4d, 5p, 6s, next 4f, 5d, 6p, 7s, next 5f, 6d, 7p, as like. Now come to the Pauli's exclusion principle. No two electrons in an atom can have the same set of 4 quantum numbers. The Pauli exclusion principle can also be stated that only 2 electrons may exist in the same orbital, and these electrons must have the opposite spin. Only 2 electrons may exist in a same orbital, but their electrons spin must be opposite. The maximum number of the electrons in the shell with parallel quantum number of n is equal to 2n square. Next come to Hund's rule of the maximum multiplicity. The pairing of the electrons in the orbital belonging to the same subshell does not take place. Same subshell does not take place until each orbital belonging to that subshell has got an electron each. It is singly occupied. So Hunsul states that the maximum multiplicity has electron with maximum multiplicity has the system with maximum multiplicity has the lowest energy. Thank you everyone. This is the end of the chapter.